In this video, we will discuss the ideal gas manipulations exercise. I'll walk you through this exercise. First thing you're going to want to do is to go to Canvas and get the handout to follow along. There'll be a place there to fill in answers to problems and also the figure that you want to look at as you're solving this problem. Here's an overview of the exercise. We're considering 1 mole of an ideal gas. You can picture this as 1 mole of helium gas. And we're looking at manipulating that gas through different pressure, volume, and temperature arrangements. We'll start at point A, which is at 5 bar pressure and 5 liters in volume, and a temperature of 300 Kelvin. Going from A to C is the isothermal expansion of the gas to a volume of 10 liters, so doubling its volume. The path from A to D is the adiabatic transition or expansion, which also doubles its volume. The path A to B is the isobaric expansion from a volume of 5 to a volume of 10. And you can see that these other points connect as well. We're going to look at each of these paths. We're going to compare A going to C directly with A going through D, then getting to C. And then finally we'll compare starting at A going to B and arriving at C. The first task is to look at each of these points, B, C, and D, and determine what the temperature would be. The graph shows you what the pressure and volume would be. And we know the starting point at A is 300 Kelvin. So can you come up with a way to figure out and calculate the temperature at each of these points? We'll start with point B. The temperature at point B can be derived by considering the ideal gas law. We're treating this system as an ideal gas, and so if you're expanding the volume from 5 to 10 and keeping the pressure at 5 bar, then this ideal gas law can be used, and the connection between the variables volume and temperature, initial and final states, is given on the screen. Use that now to calculate the final temperature T2. Pause the video and come back and check your answer. Okay, here's the answer. You should have solved for T2 in this equation, and you should have derived 600 Kelvin. In other words, the temperature needs to rise in order to keep the same pressure, since we have the same amount of gas inside the container. This temperature will be double the initial temperature because we're doubling the volume, and it would be directly proportional. Think also about the heat and work done in this process. Heat would flow in. We would say a positive Q, according to our convention. Heat would flow in, and work would be done by the gas. Whenever you're expanding, the gas is pushing back against the atmosphere and doing work on the outside. So the work is being done by the gas. That means a negative value for W. And the heat is flowing in from the surroundings. In order to heat up the temperature from 300 to 600, that heat must come from the outside. And so there would be a positive Q. We'll actually solve for these values Q and W in a moment, but for now, let's proceed and find the temperatures at points C and D. Point C should be an easy problem. This is the isothermal expansion when you're going from A to C. And so the temperature remains constant. It was initially 300, so it should be 300 Kelvin in the end. The pressure must drop. It'll be half the initial pressure, so 5 to 2.5, because again, of the ideal gas law, if the volume is doubling and the temperature is remaining the same, the pressure must have halved from the initial. We also can note that change in the internal energy of the gas is zero. If it's the same temperature, it means the energy of the gas is the same, so there's no change in the energy. This would mean that Q and W would have to be equal and opposite in sign, according to the first law of thermodynamics. There will be some heat flowing in because the work is being done by the gas. It's expanding, so it's pushing back against the atmosphere. W will be negative, and so Q needs to be positive to compensate for that, so that the total energy change is zero for the process. Let's look at point D next. At point D, we're considering the adiabatic expansion from A at temperature of 300 Kelvin to some temperature at point D that has the volume doubling from 5 to 10. So by definition, adiabatic process means that there's no heat exchange with the outside, so Q is zero. This is expansion, so work will be done by the gas. That means that the quantity W will be negative. We're going to need to determine the temperature by considering the adiabatic condition. Just like we have Boyle's law for an ideal gas at constant temperature, P1V1 equals P2V2, a very similar equation exists for the adiabatic conditions, and it merely adds a power to the volume in the equation. So pressure times volume raised to a constant is constant over an adiabatic process. That constant, shown here as gamma, can be represented as the ratio between constant pressure heat capacity and the constant volume heat capacity, which for an ideal gas has the value of 5/3. Now use this adiabatic condition to solve then for the temperature at point D. You'll need to solve first for the pressure, P2, and then you can apply the ideal gas law to get the temperature at point D. Pause the video, see if you can do that, and derive what the temperature would be at point D. Okay, I get an answer of 189 Kelvin. Compare your work to what I have here. I first solved for the final pressure. It will be 1.575 bar. You see it looks like I've drawn it in the right spot here on the graph. And the temperature then you solve for using ideal gas law, you'll get 189 Kelvin. It's worth noting that the gas has cooled substantially. That's because all of that energy that was in the gas has gone into expanding, doubling the volume, pushing back against the atmosphere, and therefore, since there's no heat coming into the system, it's an adiabatic process, all of that energy has to be put into doing the work of expanding. Let's focus now on A to C. That's the isothermal expansion at 300 Kelvin. We're going to calculate work and heat, W and Q. Our expression for doing work, at least the expansion type work, is that it's the negative integral of PdV. So see if you can solve this integral. Remember, every time we solve an integral involving a path function, it may be a different procedure that's followed. It kind of depends on how the process is done. In this case, we're keeping temperature constant and changing pressure and volume. So that will influence how we can solve for this integral. Give it a try, pause the video, come back and see if you're correct. Okay, so here's how I've solved for this integral. Because it's an ideal gas, I can insert nRT over V in place of P, and because it's at constant temperature, the nRT is a constant that comes out of the integral, and I just integrate 1 over V dV. And the integral of that is ln of V. Plugging in V2 and V1 and filling out the rest, I will get that work is minus 1,730 joules. Remember, the value of the ideal gas constant R in energy units is 8.314. And that's basically how I got to minus 1730. And I can simply write Q as being the opposite, because we know for an isothermal process, the total energy change is 0. So however much work is done by the gas, that's how much heat has to come in to the system in order to compensate for that work being done, because the energy of the gas itself is not changing. Okay, let's move on to A through to D, the adiabatic expansion. In the adiabatic expansion, we have, by definition, Q is 0. So we only need to evaluate the work in going from point A to point D. And we're going to make use of a thermodynamic cycle here first. It's a slightly easier way to solve for this quantity. We realize that if we go from A to C directly, or if we go from A to C through D, either way, we're going to have a net change in energy of 0. So I can express that as the energy change for A to C is equal to the energy change from A to D plus energy change from D to C. Since they're both 0, we can set the Q and W summation for A to D equal to the opposite of Q and W for D to C. And now here we apply a little trick. By definition, Q A to D would be 0. And also, if going from D to C, the work is 0 because there's no expansion or compression happening. And so this term at the end, the work D to C, will be 0 as well. So that leaves us with work A to D equals minus Q D to C. So we can compute the work involved in the adiabatic expansion as being the same as the heat involved in the isochoric cooling. Actually, the minus that, right? The opposite, minus Q D to C. So see if you can use that process to calculate work, and pause the video and see if you have the correct answer. Here's what I've determined for this problem. The work associated with the adiabatic expansion will be equal to minus the heat involved in the isochoric cooling from D to C. And I can compute that by just integrating CV dt for that process. The temperature change is 189 to 300. CV is 3 halves. So I have minus 3 halves R, 300 minus 189, to give us very simply minus 1380 joules for this adiabatic process. W is negative. That makes sense because we're still expanding, so we're still doing work on the surroundings. And it was kind of a trick that we did here, a very simple calculation actually, to get the work in this case by relying on an energy change for a different process. Now suppose we wanted to do this by directly integrating PDV, because we ought to be able to do that, right? Work equals minus the integral of PDV. We ought to be able to use that formula to calculate work. And indeed we can. The only thing is, solving for that integral is not all so straightforward, because in that process, A going to D, Pressure is changing, volume is changing, and temperature is changing. All three are changing. So there's nothing that comes out of the integral as a constant. We have to apply the adiabatic condition where P times V to the gamma is a constant. So substituting in P, we can plug in PV to the gamma over V to the gamma, and then pull out the PV to the gamma as a constant. That leaves us with the integral of 1 over V to the gamma. If I use my antiderivative formula, that gives me V to the minus gamma plus 1 over minus gamma plus 1. And I can evaluate that at the endpoints 10 and 5 and do the subtraction there. And I'm also going to need to multiply by 100 because the units here, since we're dealing with pressure and volume, will come out to be liter bars. And liter bar is an energy unit. But if you want to convert to joules, you'll have to realize that there's 100 joules in every liter bar. So that's why I multiply by 100 in the end, and I will get minus 1380 joules doing the integral this way. Notice that that agrees with doing the shortcut method. I like the shortcut method better. It's a little more straightforward, but it's good to see how these things all even out here. We can either solve this integral for work, or we can use the first law of thermodynamics to solve for the work of the adiabatic expansion. Next up, let's start at A and go to B. That would be an isobaric expansion. We've already determined that the temperature rises to 600 Kelvin. How can we compute Q and W for that? Well, again, for the work, we can use the same formula, minus integral PdV. Now, the work involved in solving an integral will be a little different because this is a constant pressure process. So think about how you would do that. And I'll go ahead and give you also the formula for Q in this case. Since we're doing this at constant pressure, we would simply integrate the constant pressure heat capacity over the integral dt. So see if you can apply these two formulas to calculate W and Q for the isobaric expansion of an ideal gas. And I'll come back in a second, pause the video, and we'll have the answer. Okay, here's what I've worked out for W and Q for this case. Because it's constant pressure, you can pull the P out of the integral, and you just have the integral of dV, which is V2 minus V1. Filling in the numbers, 5 bar and then 10 minus 5 liters gives you 5 liters. That's 25 liter bars. And we multiply by 100 to convert the liter bars to joules, just like we did in the last problem. That'll give us minus 2,500 joules for the work involved. The heat, the Q in this case, can be found by plugging in 5/2 R for the constant pressure heat capacity. The integral of dt is simply T2 minus T1. Plugging in our values of 600 Kelvin and 300 Kelvin, we'll get plus 6240 joules for the heat. So there's lots of heat going in. That's positive Q, so the heat's going in, and work's being done by, but there's more heat going in than the expansion is requiring, and therefore the temperature rises. The rest of that heat goes into just heating up thermally the gas from 300 to 600. Now for the processes remaining, the B to C and the D to C, these are both isochoric, meaning constant volume. And so the work would be 0 for both of those. And we can get the heat by simply integrating the constant volume heat capacity over the temperature integral. So that's very easily done. We get minus 3740 for the B to C process, and positive 1380 for the D to C process. This number we had before, right? Because we used that when we used the thermodynamic cycle to calculate the work involved in the adiabatic expansion. So let's sum this up. First, let's consider all of the energy changes, the total energy changes for each of these paths. And going from A to C, no matter which route, the total energy remains constant. So if you go directly from A to C, it's a change of 0 joules. But if you go through D, you initially, the gas is going to lose 1380 joules, but then in the process of heating back up to a temperature of 300 Kelvin, it'll gain 1380 joules. In the other direction, when we're going from A to B, the isobaric expansion, the energy of the gas is going to increase. It's going to go up by 3740. And then in order to reach C eventually, we're going to have to lose that additional energy that we gained, minus 3740. These numbers can be verified. You should verify them by simply adding Q and W together that we computed before for each of these routes. We can sum up the picture for heat as well, and that's a little interesting to consider, right? When we go directly from A to C, that involves heat flowing in to the gas, positive 1730 for Q, and all of that heat is directly involved in expanding the gas. It leaves the gas at the same temperature. It doesn't heat up the gas at all. Now, if we go through D, the first step, the adiabatic transition, doesn't involve any heat. And going from D to C is where we pick up that 1380 heat. And the final route, if we go through B to get to C, we initially have to suck in over 6,000 joules of heat, and then we release some of that back when we cool it back down to 300 Kelvin. So in each route, the heat pooled is the same as the work done overall, so that the first law of thermodynamics is held. But as you can see, depending on how we do the expansion, we could, at a minimal, draw in 1380 joules of heat, or at a maximum, we could draw in 2,500 joules of heat. So depending on how we do this transformation, even though in the end we're just going from A to C, the beginning's the same, the end's the same, but the route's different, and that means that potentially we've done something different to the environment. We've pulled a different amount of heat out of the environment for each of these processes.